So in this lecture we are going to discuss tensors, covariant and contravariant tensors. So we will define tensors at the end of this lecture because it will become difficult to understand tensors without discussing some examples of them before going into its definition. So first of all we will discuss change of basis. Change of basis of a vector space. Let us take a vector space V with dimension of V to be n, and we take a basis for this. For simplicity we consider V to be R2, which is simple two-dimensional vector space. So it can be represented in this manner. Let me say x is here and this one is y axis. I can take a unit vector over here and represent this with x cap and this one with y cap. Now if I change the coordinate system or I change the basis, so it will become in this manner, and let me call this x prime and this one y prime. So now there are two basis systems, one is the xy basis system and the second one is the x prime y prime basis system. I can express the new basis in terms of the old basis. This one will have basis x prime hat and y prime hat. So I can express this new coordinate system in terms of the old coordinate system using some relations, because this vector can be expressed as a linear combination of this vector and this vector, and similarly this vector y prime can be expressed as a linear combination of this y cap and this x cap. So I can do this very easily, which means that I can write x prime cap is a linear combination of x cap y cap. So this will become, let me say, a11 x cap and a12 y cap. Similarly I can write the new y prime in this manner, a21 x cap plus a22 y cap, and this means I can write this also in this manner in terms of column vector. This will become a11 a12 a21 a22 and what will come here, x cap y cap. So just by multiplication of this matrix we can obtain the new basis system in terms of the old basis system, and now we call this matrix R matrix, and this is actually the change of basis matrix. Change of basis matrix. So in column vector form I can write this in this manner, x prime y prime unit vector R into x cap y cap, and similarly in the row vector form I can safely write this in this form, x prime hat y prime hat. This will become x cap y cap multiplied by R. So we can do this, and this will be actually the transpose of this matrix, because I have taken the transpose of left and right hand sides. So one is the row vector form, the other is the column vector form. Now if we generalize this concept to the n dimensions, so let me say if I have a vector v with dimension n, and let me say one of the bases is b, which has as basis vectors b1, b2 up to bn, and there is another basis for the same n-dimensional vector space, I call that b prime. So that will become b1 prime, b2 prime up to bn prime. Now I can express the new coordinate system b prime in terms of the old coordinate system b by multiplication with matrix R, where matrix R is the change of basis matrix. I can use this equation to go from one basis system into another basis system. Now if I change the basis system, so everything that depends upon the basis will also change. For example, a vector, the components of a vector will change according to the change of basis. So for example, let me say if I have this coordinate system and then this x cap, y cap, and then there is another coordinate system which is here, x prime, then this is here y prime, and I have a vector, let me say the vector is over here, a some vector. Now this vector will have one representation in terms of xy coordinate system, which will be in this manner, and in terms of the second coordinate system it will have components which will be different. So now the question arises, if I know the change of basis, we know the change of basis matrix, then how can I transform the components of the vector from the old components into the new components? We know R, then how we can find the components of the vector, in the new basis from the non-components in the old basis. So that is the question that we have to answer in the old basis. Okay, so this is the question that we have to solve. So let us generalize everything, and then we will see what happens. So let me say we have some vector in the old coordinate system. I have v vector in the old basis, which is actually the unprimed basis. So I will have the vector in this form, and let me remove this symbol because now I am in the n dimensions. So this will become this vector v in the old coordinate system will become vi and then its component in the old basis, and then there what will come here, bi, and this will be summation. If you consider the Einstein summation, then we don't need to write this like this, no need of this summation symbol. So VIB is the ith. What is this notation? Ith component of V in basis B. If we consider basis B, then what will be the ith component of this? That is represented by VIB. Or you can write this also in this manner. V becomes equal to, if I expand this, V1 in basis B, B1, or plus this summation will go up to Vn basis B, and then Bn will come here. Okay, so I can write this also in this manner. If the V vector is in the row vector form, so I can write this by multiplication of row vector basis B multiplied by V representation of V in the basis B. So I can write this in this manner. So now again this vector V can be also represented in the new basis, which is actually B prime. In B prime basis, V will become, the same equation will be there. Now the summation over I and ith component of this in B prime basis, and then what will come, B prime I will come here. So I can write this V also in this manner. B prime, this is the row vector, and V is also in the row vector form, in representation of multiplication of this with V B prime, because this is now its representation in the new coordinate system. And what is this VB? Let me say VB, we can write this VB in this manner. We define this. This is V1B up to VNB. And similarly VB prime will become equal to V1 B prime to VNB prime. So we have these equations. Now remember that the new coordinate system B prime can be expressed in terms of the old coordinate system, old basis B, and multiplied by the change of basis matrix. We have this equation, we have done this previously. So this is the multiplication symbol. Now if I apply this equation, so what will I get is this, V is equal to B VB, and similarly the same vector is represented in the primed coordinate system B prime, and then this VB prime. So this will become equal to BVB So now this will become B prime VB prime and this B can be written as B prime R inverse VB, because from here you can see that B is equal to B prime R inverse. So now these two will cancel, so you can see that this equation gives me VB prime is equal to R inverse VB. So this is our final equation. The coordinates in the new prime basis will be related. So these are the coordinates in the new prime basis, and this one is in the old basis B. So they are related in this manner. They are multiplied by R inverse. You can see here there is R inverse. So it means that the coordinates in the new basis will transform inverse to the change of basis matrix. So I multiply by R inverse instead of R, and R inverse is the inverse matrix of the change of basis matrix. So such vectors whose component transformed inverse to the change of basis vectors, we call them contravariant vectors. Contravariant vectors. These are vectors whose components transform inverse to the change of basis matrix. So this means that in component form I can write this also in this manner. The primed components, say Vi in B prime in the prime coordinate system. You can also for convenience put a prime here, which means this is in the primed coordinate system. These will become equal to R inverse Ij and then Vj in the unprimed coordinate system. So this is in components form. This formula is for the, this is in the components form. So you can find the ith component in the new basis, in the prime basis, in terms of the components in the old basis, and with the help of these transformation, change of basis matrix, inverse of change of basis matrix. So such vectors are called contravariant vectors, and for notation convenience you must remember that contravariant components have index as superscript. You can see here that we are putting the index over here, Vi. So this is in superscript. This means this component is actually contravariant. And you can remember this from here, that this n contravariant, this n is upward. So the upper part of this n is actually felt. So what will come here? For just for remembering purpose, the index will be at the upper as a superscript in the case of contravariant vectors. Okay. So all those things which transform inverse to the change of basis matrix, those will be called contravariant vectors or contravariant tensors, but we will go to the tensors at the end. Now, what are the examples of contravariant tensors? So you can see that in case of position vector, if you take position vector capital R, so let me say x cap plus y cap plus z cap, all these coordinates x cap, y cap, z cap, they transform inverse to the change of basis matrix. So which means all these components are actually contravariant. These are contravariant components. So now all the let me say if we take velocity, so velocity is just derivative of position vector or displacement. So velocity is also contravariant. This is the first example. This is the second example. Similarly, acceleration is the rate of change of velocity. So it is also a contravariant tensor or contravariant vector. And similarly, if you take momentum p, so that is mass times velocity, so that will be also become a contravariant tensor or vector. So in general, all those vectors which transform in opposite manner to the change of basis, they will form contravariant vectors. So now we come towards covariant vectors. Covariant vectors. Okay, so the transformation which is here, such transformation in the previous case is called contravariant transformations. Now there are also vectors which do not change in inverse manner to the change of basis, which means those vectors change in accordance with the change of basis matrix. So we have R matrix, which is actually the change of basis matrix, and in covariant vectors, for the transformation into the new components, the old components change according to this R matrix. They don't go into the R inverse. They don't take R inverse in their multiplication. So let us study them. One example, or for easiness purpose, we can take linear functionals. Now, what are linear functionals? These are also called linear forms. So, linear functions actually take linear functionals actually let me say if alpha is a linear functional, so it will be a map from the vector space to the field over which this vector space is formed, which means real or complex numbers. So I am considering here real numbers. We can also take complex numbers. So such linear functionals will have components and these components will be different in different basis systems, which means that they will change if we change the basis system. So let me say the ith component in the basis B will become alpha I in the basis B, or let me write it here because these are actually covariant. We will see at the end that these vectors are covariant. These components are actually covariant. So alpha IB will become, what will be this, the definition of this? The component of alpha that we obtained after we apply alpha on BI. So this will be, the alpha IB will be obtained from the action of alpha on the basis vector BI in the old coordinate system. So now in the new coordinate system, definitely this will become alpha I B prime will become equal to alpha, the action of alpha in the new coordinate system in BI prime. So this will be the situation. Now I know that we have this relation that the new basis is actually the old basis multiplied by the change of basis matrix BR. So actually matrix. And this also means that in the row vector form, actually this can be expressed as in this manner: BI RI1 and similarly BI RI2, and this will go up to BI RIN, which is nothing else but actually this thing, B1 prime, B2 prime, and this one is Bn prime, which is the same old statement that the new coordinate system can be expressed as a linear combination of the old coordinate systems. Okay. So now I write it in this manner that let me write alpha I in the old coordinate, new coordinate system. So this will become equal to alpha, the action of alpha on BI in the new coordinate system, and then I can write this also in this manner: BI prime is nothing but summation like this, BI RI, and let me use this symbol J here or L here. This is L, this is L, because this will become summation, so I can use any symbol, and I will come here. This is from the previous, this equation, in this equation 1, so it is from equation 1. Now because this alpha is a linear functional, so I can write this, I can take this BL which is a constant, this RLI which is a constant outside, and this will become RLI alpha BL and this means that summation RLI. Now alpha BL is actually alpha L in the B coordinate system. So alpha I, this is on the left hand side. Now what does this mean? What is this? This is actually the component of the function in the B coordinate system or the B basis, while this one is the component of the alpha in the prime basis. So I obtain the component of the functional in the prime basis from the component of the function in the simple basis or in the old basis just by multiplying the components of the transformation matrix. So this means in this summation is obviously over L because it is repeated over here. So this means that I can find the components of the new vector in terms of the old vectors, components of the old vector, just by multiplying by the elements of the change of basis matrix, which means R matrix. So these types of vectors are called covariant vectors. In matrix form, I can write this in this manner, that alpha in the B prime coordinate system or B prime basis will become alpha in the B basis multiplied by R. So you can see that we have R instead of R inverse here. So we have R over here, and that means that such vectors are actually covariant vectors. So a linear functional is a covariant vector. In column vector form, this R will come before alpha. So alpha is actually a linear functional, or we can say alpha is a covariant vector. Because it changes, it transforms in agreement or in accordance with the change of basis matrix. So such vectors are called covariant vectors. Okay, so everywhere in linear algebra or in mathematics, if we see some quantity which changes according to the change of basis matrix, then we call such an object a covariant vector. And we use subscripts for this instead of superscript. So for example, if alpha has the component I, so I write it here as a subscript, because so you can remember this because this V has this lower part filled. So therefore we put here, we make this notation that in the case of covariant components, the index for those components will be as a subscript instead of superscript. Okay, so now These we studied contravariant vector and covariant vectors. So, contravariant vector transform in inverse to the change of basis matrix, and covariant transform to the according to the change of basis matrix. And you can see that they can be indexed by a single variable, by a single index. They have components which need a single index, or they can be indexed by a single number. So, we called such vectors, or we can also call them tensors, and the notation for these type of tensors is this PQ. The first one is for contravariant, and the second one is for covariant. So, if we take for example a vector, so vector is a tensor. We haven't defined it tensor, but you must remember that vector is also a type of tensor, and this tensor is actually contravariant. So, it can be indexed by one index, and there is the covariant component is 0, which means vector has only the components of the vector are contravariant. So, in case of contravariant, they can be indexed by one index, so only one will come here, and there is no covariant component, so this will become 0. Linear functional, on the other hand, is 0-1 tensor, and this means that we have the covariant, the contravariant part is 0, contravariant part is 0, it has no index, and it can be addressed by a single index, covariant index. So, this becomes a 0-1 tensor. So, we stop our discussion here, and in the next part we will go into the further details of the tensors. Okay, so you can watch the second video to go in the further higher order tensors.